Hello and welcome to my short video about matrices and how they can be used to analyze social connections in a network. I'll start by briefly discussing the history of matrices. So a matrix is simply a two-dimensional array of numbers in a square or rectangular form. While the term matrix was introduced by English mathematician James Sylvester in 1850, the concept was already being applied to solve agricultural problems in ancient China during the Han Dynasty. The process is actually identical to what Europeans would later call Gaussian elimination, with the only difference being the direction that it should be read in. The formal European theory of matrices was later developed by a German mathematician named Gottfried Leibniz in the 17th century and was expanded on further by Carl Gauss during the late 18th century, who worked on matrix multiplication and inverses of matrices, as well as rediscovering Gaussian elimination. Gaussian elimination involves reducing a matrix to triangular or row echelon form by eliminating most numbers to zero, which is accomplished using elementary row operations like adding or subtracting one row from another or a multiple of one row from another. Matrix addition and subtraction are relatively straightforward. This requires the matrices that are being added or subtracted to be of the same size, and then simply add or subtract the numbers in the corresponding positions in both matrices. Matrix multiplication is a bit more complicated and involves a dot product method. So unlike in matrix addition and subtraction, matrices of different sizes can be multiplied with one another, provided that the number of columns in the first matrix is equal to the number of rows of the second matrix. The method to do so goes like this. The first position of the new matrix C, so position C1, is obtained by adding the products of elements of the first row of matrix A and the first column of matrix B, then repeat with the first row of matrix A, but this time with the second column of matrix B to obtain the value for C2, and so on for the rest of the matrix. Now, while matrices are used in a huge number of practical ways, I'm going to focus on their uses in social network analysis. Obviously, this applies to social networking sites like Facebook, but I'm going to focus on dating websites or dating apps in this current example. I think a topic like this is interesting as it allows us to quantify ideas about social structure and individuals' roles and positions in such a structure using mathematical language. So the matrices that are used in this kind of analysis are called adjacency matrices, and they essentially represent connections between nodes of a network, and in this case, the nodes represent people. So for this example, we'll use three men numbered 1, 2, and 3, and three women numbered 4, 5, and 6, and represent these connections between them through an adjacency matrix. These matrices typically have only ones and zeros, where a number 1 indicates a match between two people. More generally, what a number 1 in the matrix actually represents is the number of pathways of length 1 between two nodes. In this example, each path between two people represents a mutual match where the users have chosen to like each other's profile. So each pathway goes in both directions. The diagonal or the trace of the matrix here is full of zeros since the user can't match with themselves. Now, because these connections represent a fully mutual predicament, the adjacency matrix is symmetrical in the diagonal, and this also means that this matrix, when transposed, is the same as the original matrix. However, this would not be the case if the connections between people were not fully reciprocal. For example, if our matrix was representing a situation where man 1 liked the profile of woman 5, but she did not like him back, the matrix would no longer be symmetrical in the trace, and therefore would not be a transposition of itself. We can therefore say that the correlation of an adjacency matrix and the transpose of that matrix can show us the degree of reciprocity of the ties or connections between the nodes. Now, going back to our original matrix with the fully mutual connections, we can now see how multiplication of the matrix by itself can provide us with further insights into this small network. If we take the adjacency matrix squared, the numbers we now see represent the number of pathways of length 2 between people in the network. This means that this matrix shows us how many mutual connections any person has with any other person. For example, man 2 and man 1 aren't matched with any of the same women, while man 1 and man 3 have both matched with woman 5 and 6. So what about the trace now? Well, the trace now shows us how many pathways of length 2 a person has with themselves. And in practical terms, this means it shows how many matches they have in total, given that these pathways go to another person and then straight back to themselves. So man 3 has a number 3 on the diagonal to represent their 3 matches in the network. Multiplication of the original matrix to the power 3 will show us the number of pathways of length 3 between people in the network, and so on. So it's clear that simple manipulation of adjacency matrices can yield powerful insights about the structure and dynamics of social networks in different domains. In addition to their use for dating apps and social media companies, this form of analysis can also be applied to business networks, where it can reveal hierarchies and help to optimize workflow. It can be applied to security and policing, where it can be used to understand criminal networks and identify potentially dangerous individuals or groups. Or it can be applied to epidemiology, where it can help to model networks to track the spread of disease. That is the end of my presentation. Thanks for listening, and I hope you found it interesting.